Swayam Prabha. Digital India. Educated India.
In the module on matrices, we have talked about lots of results relating to various properties of matrices, types of matrices. One of the fundamental results that is enduring in the applications of linear algebra to data analytics is that spectral decomposition of real symmetric matrices. We have already talked about it, but we did not go into the proofs and claims of some of the results that we often need. So, I am going to fill the gap. So, this is a part of the module on matrices. So, you can think of linear algebra consisting of two sub modules. One is linear vector spaces, another is matrices, and I am now talking about a result in this module relating to matrices. We have already seen many of the properties. Now, I want to add some mathematical results for those of you who want to understand. So, let A be a n by n real matrix of order n. If there exists a scalar lambda real or complex and a vector v real or complex, if lambda is real, v will be real. If lambda is complex, v has to be complex such that A v is lambda v, then lambda is called the eigenvalue and v is called the corresponding eigenvector. We have already seen this. Why are we seeing this now? I am going to give you some of the properties, prove some of the properties. The pair lambda v satisfying are called eigenpair. The set of all eigenvalues of A is called the spectrum of A. Let xk be a set of k eigenvalues. I am sorry, let Sk be a set of vectors which are linearly independent vectors in Rn. That means, each vector v1, v2, vk, they are all vectors in Rn. So, I am considering a set of k linearly independent vectors in the set Sk. The k refers to the number k of vectors in here, and one of the properties of the vectors is they are linearly independent. The span of xk denotes the set of all linear combinations of vectors in Sk. The span of xk is a k dimensional subspace of Rn. Please understand, if I have one vector that is already linearly independent. So, what is the span of a vector? Is the line through the vector. If I have two vectors that are linearly independent, that means the angle between them is not 0, then they define a plane. So, the plane is the span of the two vectors likewise. So, Ax, so what is Ax? Ax belongs to the span of x for any x belonging to Sk. Any x must be belonging to Rk. So, if I pick a k dimensional vector x and multiply A by x, that belongs to the span of xk, because it is. Look at this now. I want you to be able to, I want to go a little bit slow on that. So, we already saw the notion of a linear dimensional subspace. Now, I am going to talk about what is called the invariant subspace. So, let x be a vector in the span of xk. So, what does it mean? Xk consists of vectors v1 through vk. Span of the Sk refers to linear combinations of the set of vectors in Sk. So, xk belongs to the span of xk. If I multiply x by a, it also belongs to the span of xk. then we say xk is A invariant. That means if I pick a vector in sk and multiply the vector by A, the multiplied vector, the resulting vector coming out of the multiplication also belongs to the same space, then we say that space is an invariant subspace. Now, why is this important? If I say AV is equal to lambda V, that means multiplying a vector V by A simply scales the vector by a constant without changing the direction. So, AV belongs to the span of V. So, that means every eigenvector defines an invariant subspace of dimension 1. So, that is a new way of looking at the eigenvectors. So, there are a couple of concepts already involved in here: square matrix, eigenvalue, eigenvectors. Eigenvectors can be real or complex, the definition of an eigenvector, the notion of an invariant subspace. So, rewrite one as a linear homogeneous equation, A minus lambda I V is equal to 0 as equation 2. Equation 2 is a homogeneous equation, it has a non-null solution exactly when the matrix A minus lambda I is singular, that is P lambda is equal to determinant of A minus lambda I is 0. So, the n value eigenvalues of A are given by the n roots of the characteristic polynomial P lambda of A, which is given in 3. So, now I am going to talk about the distribution of eigenvalues of A. Since A is real, the coefficients of the characteristic polynomial P lambda are also real. An nth degree polynomial of degree n has n roots. The roots are real or complex, and the complex rule might occur in conjugate pairs, and that comes from what is known as the fundamental theorem of arithmetic. A typical distribution of eigenvalues, look at this now, this is the real and imaginary axis, this is the x axis, the real axis, y axis, the imaginary axis. So, I can eigenvector in -4, eigenvector complex conjugate, there is one eigenvalue which is 0, there are two complex conjugate eigenvectors, eigenvalues on the y axis, imaginary axis. So, in general, the spectrum of A could be anywhere in the complex plane, provided the complex roots are conjugate. Now, I am going to talk about eigenpairs of real symmetric matrices. So far we talked about a general matrix A, its eigenvalue, eigenvectors, each eigenvector being an invariant subspace. Now, I am going to bring in the notion the matrix is not only real, but also symmetric. If A is an n by n matrix, symmetry means A transpose is A, that means is that part of the matrix above the diagonal and below the diagonal are identical. So, there are several properties of eigenvalues of symmetric matrices, which I are going to not only recite, but also prove. So, SM1, the first property of symmetric matrices, eigenvalues of a real symmetric matrices are real. That means eigenvalues of a real symmetric matrix cannot be complex, it has to be real. Eigenvectors corresponding to two distinct eigenvalues are orthogonal. Wow, symmetry is a very powerful property. Symmetry restricts the eigenvalue to be real. Symmetry restricts the eigenvectors to be orthogonal. If lambda is the root of P lambda is 0, in 3, the eigenvalues can be of multiplicity. For example, if I have an equation x minus 1 whole square is equal to 0, x is equal to 1, 1 twice is a second degree polynomial, right? It's a second degree polynomial. It has two roots. It can be multiple roots. and the roots can be repeated. So, if lambda is a root is of algebraic multiplicity, then there exists k mutually orthogonal random vectors such that lambda I V I is an eigenvector pair of A. So, I am going to introduce two kinds of multiplicity. One is called the algebraic multiplicity, another is called the geometric multiplicity. Algebraic multiplicity of a root is the number of times the same root is going to be able to, is the same lambda is going to be the root of p lambda. For example, if I can write p of lambda is equal to lambda minus 1 square times q of lambda, and if this term is 0, this can be 0 when lambda is 1, 2 times. The rest of the root come from solving q lambda. Solving q lambda. I hope you are with me now. So, algebraic multiplicity is the number of times that the same value lambda is going to be able to solve the polynomial equation p lambda is equal to 0, roots of the polynomial. Each eigenvalue corresponds to an eigenvector. There exists a set of k mutually orthogonal eigenvectors v1, v2, vk such that lambda I V I is an eigenpair, eigenvalue, eigenvector, eigenpair. So, lambda V I is called an eigenpair. If the k eigenvectors corresponding to the k distinct eigenvalues are linearly independent, that is, then k is also called geometric multiplicity of dimension of the invariant subspace spanned by this. That means, the same eigenvalue induces k eigenvectors such that the dimension of the invariant subspace is equal to k. The dimension of the invariant subspace is called the geometric multiplicity, that comes from the property of eigenvectors. Algebraic multiplicity comes from the eigenvalue lambda being the number of times it is going to be the roots of the original polynomial equation p lambda. If lambda I V I is such that A V I is lambda I can now combine all the vectors V into one matrix, V i's into one matrix, lambda into one matrix. I can rewrite all of them simultaneously as A V is equal to V lambda. The eigenvectors of a real symmetric matrix are mutually orthogonal, and how do I represent mutual orthogonality? I'm sorry, I think we have replaced this. This must be equal, this must be not equal. Oh, I say that's I think that's correct. V I transpose V j is not equal to 0 when I is equal to j, and V I transpose V I is equal to 0 otherwise. So, what does it mean? Two distinct vectors otherwise means I and I not equal to j, two distinct vectors are orthogonal. If you take the inner product of the vector with itself, it is not 0. If V i's are unit vectors, the inner product of a vector with itself is 1. So, such a property of eigenvectors is mutual orthogonality. Again, I am taking this for granted. I am going to show you some of these properties very quickly. Orthonormality of the eigenvectors. Why do we assume without loss of generality eigenvectors can be orthonormal? A V is equal to lambda V. So, if I multiply both the equations by alpha, for any alpha non-zero, we need only consider, look at this now. I can multiply V by alpha comes in here. So, whenever I multiply V by alpha is preserved. What does it mean? I can choose alpha to be 1 over norm of V without loss of generality. Therefore, from now on, I am going to consider only eigenvectors which are unit vectors. If eigenvectors are unit vectors, then the inner product of two vectors that are not equal is 0. If two vectors that are equal, that is equal to 1, that is called orthonormal system of vectors. Hence, V is an orthogonal matrix. So, V transpose V, this is V transpose, this is a outer product matrix. Because of the orthonormality of this, the diagonal entries are all 1, the off diagonal entries are 0. So, this is the this is the identity matrix. You can also verify this is VV transpose. Multiplying both sides by V transpose and using 7, we now see A is equal to A VV transpose, which is V lambda V transpose. This is called, this is a multiplicative decomposition. This is called the eigen decomposition. This is also called spectral decomposition. Spectral decomposition. So, what is the spectral decomposition of A? A now is the matrix, another matrix, this is the matrix. So, you can think of it as lambda times VI VI transpose. VI VI transpose is a rank 1 outer product matrix. Therefore, I am able to express A in 2 ways. One is V lambda V transpose, this is the multiplicative decomposition. This is an additive decomposition where this is a rank 1 matrix, they are weighted by the eigenvalue. So, it is a sum of a weighted sum of rank 1 matrices, weighted sum of rank 1 matrices. Now, a little digression. Let H be a vector, let X be another vector, X bar be an orthonormal, an orthogonal projection of X along K. The unit vector along H is H over the norm of H. The orthogonal projection X bar of X along H is given by. So, X bar is simply the inner product of X transpose H bar. H bar is the unit vector. So, this is the constant times H bar. So, this matrix product is associative. So, X transpose H bar is H bar transpose X. I can multiply a vector either on the left or on the right. So, this is the constant, I am now pulling it to the right. So, if I did that, it is H bar transpose X, and this is the rank 1 matrix, and that is the projection matrix, is an orthogonal projection matrix. Therefore, X bar is simply the projection X bar is equal to PH times X, the notion of an orthogonal projection matrix, PH induced by the unit vectors H bar along the direction H. That is an important concept. Consequently, rank 1 matrices, which are VI VI transpose, are orthogonal projection matrix along VI. So, in analogy with HI, VIs are already orthonormal. VIs are already orthonormal. So, each of the VI transpose is a rank 1 matrix. That is, 9 expresses A as a linear combination of orthogonal projection matrices. Let us look at that now. This is the sum of n distinct orthogonal projection matrix. Now, we are going to go to symmetric and positive definite matrix SPD. In this case, eigenvalues are real and positive. So, for the general matrix, eigenvalues can be real or complex. For symmetric matrix, eigenvalues are real. For the real and positive definite matrix, the eigenvalues are real and positive. In that case, I can express lambda to be equal to lambda to the power half, lambda to the power half. Lambda to the power half is a diagonal matrix whose diagonal elements are the square root of the diagonal entries. So, A is equal to V lambda A is equal to V lambda V transpose. So, this can be written like this. Now, if I define this as a matrix V bar, this is equal to V bar transpose. So, this is another form of the eigen decomposition. This form of decomposition we will soon see later looks like the so called the Cholesky decomposition, but these two are different. Now, why do we concentrate on symmetric positive definite matrices? In multivariate statistical analysis, SPD arise naturally as covariance matrices. Please understand, data science is largely multivariate statistical analysis. SPD matrices arise naturally in data science as covariance matrices of large matrices, covariance matrices of data. In fact, many of the well-known methods in multivariate statistical techniques such as PCA, singular value decomposition, canonical correlation, they are all based on spectral or eigen decomposition of matrices. We will soon later see PCA, SVD. Canonical correlation I am not planning to do in this course, but you can refer to it, the use of symmetric positive definite matrices in canonical correlation. Now, I am going to quickly go over the appendix where we are trying to prove some of the claims. The goal of this appendix is to provide a proof of the various properties of real symmetric matrices used in the development of this module. The final result is to prove that every real symmetric matrix is diagonalizable using orthogonal transformation. Look at that now. That's the ultimate goal. If I have a matrix A which is A transpose symmetric, what is it we want to know? I can express A to be lambda. I want to be able to express A to be converted into a diagonal matrix. So, this is the given dense matrix, this is the world of diagonal matrices. I want to be able to map any matrix to its diagonal form, that is called diagonalizable matrices. That every symmetric matrix is diagonalizable. If every symmetric real matrix is diagonalizable, symmetric positive definite matrices are diagonalizable, and this diagonalization can be achieved through what is called orthogonal transformation. One such transformation is the eigen decomposition. AV is equal to V lambda, therefore, V transpose AV is equal to lambda. So, this is an example of a matrix A being reduced to a diagonal matrix lambda. Existence of eigenvalues and eigenvectors. If A is a real symmetric matrix of order 2 or more, the characteristic polynomial is given by the determinantal equation in 14. The determinant of A minus lambda I must be 0. Then there exists at least one real vector that lies in the null space of A minus lambda I. The null space of A minus lambda I in mathematics is also called kernel. So, null space of A is also called kernel of A, kernel or null space. And what is the null space? It is the set of all vectors x such that Ax is equal to 0. So, what does it mean? If lambda is an eigenvalue, lambda minus Ai is a matrix. This matrix, what is this matrix? It is a shifted matrix. A is shifted by lambda I. It subtracts a lambda from the diagonal matrix. This shifted matrix has a null space, and the elements of the null space are the eigenvectors of the matrix A. So, that is what I want you to be able to understand. If let A be a symmetric matrix of order n greater than or equal to 2, the characteristic polynomial has a degree n must have at least one solution, say alpha. The characteristic polynomial must at least have one solution, means what? An nth degree polynomial must have n solutions. All the solutions can be coincident. So, it must be at least one. For example, if I take A to be an identity matrix, what is the eigenvalues of identity matrix? All are ones, and so n is a eigenvalue of multiplicity n times, and we already know identity times EI is equal to 1 times EI for 1 less than I less than n. So, 1 is an eigenvalue of algebraic multiplicity n. The geometric multiplicity relates to the set of all eigenvectors. So, every unit vector is an eigenvector of I. So, this is the case where algebraic multiplicity, geometric multiplicity are equal, is an example. In this case, 1 is also a multiple eigenvalue where the algebraic multiplicity is n. In general, I can factorize a polynomial. If a polynomial can be factorized, please understand the polynomial A minus lambda I is equal to 0, p lambda is called a monic polynomial. What is a monic polynomial? A monic polynomial is one whose largest, the coefficient of the largest degree term is 1. For example, if I have a matrix A is equal to A, B, C, A, B, B, C, the p lambda is here is equal to A minus lambda times C minus lambda minus B square. So, if you multiply lambda, the lambda degree is equal to lambda square minus A plus C lambda minus B square minus B square plus AC. So, lambda square has a unit coefficient. So, in general, the characteristic polynomial is a monic polynomial of whose coefficient of the leading term is 1. So, the notion of a polynomial, monic polynomial. So, p lambda can be expressed as the product of powers of monomials. So, lambda is an algebraic multiplicity Ni. Ni is the algebraic multiplicity of lambda I. Ni plus n1 plus n2 plus nk must be equal to n. The number of distinct eigenvectors Mi corresponds to the eigenvalue lambda I are called the geometric multiplicity. So, the number of eigenvectors, so let us say lambda is an eigenvalue of algebraic multiplicity Ni. It has Mi distinct eigenvectors corresponding to Ni values. This is called the geometric multiplicity, this is called the algebraic multiplicity. In general, the geometric multiplicity is less than or equal to the algebraic multiplicity. But when A is symmetric, the geometric multiplicity is equal to the algebraic multiplicity. The identity matrix is a symmetric matrix. Therefore, its geometric multiplicity of the eigenvalue, the eigenvectors E1 through En is n. The algebraic multiplicity of the eigenvalue 1 is also n. And that happens for all k eigenvalues. So, this is the special property of the symmetric matrices. Now, I am going to show the few of the claims. The eigenvalues of a real symmetric matrix must be real. You remember, I have already quoted this, now I am going to prove this, claim 1. Sometimes you keep using some result, but you need to know where it comes from. So, that is what I am trying to fill in here. Let lambda v be an eigen pair of A, that means AV is equal to V lambda. I want to show things are real, so I am going to pretend it may be complex. If it is complex, I should be able to take complex conjugates of both sides. I know A is a real matrix, lambda is an eigenvalue, V is an eigenvector, both could be complex. So, let V bar lambda bar be the complex conjugate of V and lambda respectively. So, A V lambda is one relation. The relation 17 is obtained by taking the complex conjugate of 16. Now, I am going to multiply the left hand side of 16 by V transpose and that of 17 by V, okay, the left hand side of 16 by V bar transpose and that of 17 by V transpose. So, in that case, I am going to get V bar transpose AV, V transpose AV. Now, please understand, A is a symmetric matrix, these two quantities are equal, so the difference is 0. By virtue of the eigenvalues, I get this is lambda times V bar transpose V, this is lambda bar times V transpose V bar. So, V bar V transpose V bar, they are essentially the same because A transpose B is equal to B transpose A. Therefore, the common value lambda minus lambda bar. Now, please lambda minus lambda bar. So, this is a real number. Why is the real number? A bar. If A is equal to alpha plus I beta, if A bar is equal to alpha minus I beta, that is equal to A square plus B square. You already know. So, therefore, the product must be 0 and this is not equal to 0 because we know V is not a 0 vector. So, V transpose V bar is greater than 0. So, the only way this can be 0 is these two are equal. If lambda is equal to lambda bar means what? A number and its conjugate are the same. If the number and the conjugate are the same, it must be real. So far I have assumed this result. For the first time I am going to show you, I am proving that the eigenvalues of a real complex, eigenvalues of a real symmetric matrix must be real. So, you need to augment your understanding by proving some of these results like this. What is the claim 2? Eigenvectors corresponding to different eigenvalues of a real symmetric matrix are orthogonal. We have used this fact, now I am going to verify this, I am going to prove this. I hope you understand the importance of these results. We are going to flood the future analysis by quoting these results. So, early on I am trying to provide proofs of these results. Let lambda V and mu u be the eigenpairs of a real symmetric matrix, where lambda and mu are two distinct eigenvalues. Please understand, any matrix, any real symmetric matrix A must have at least one root. I am assuming, and we have already shown they must be real. So, lambda and mu be two real eigenvalues and let them be not equal. So, what is the claim we want to do? The eigenvectors corresponding to different eigenvalues of a real symmetric matrix are orthogonal. So, lambda is not equal to mu, lambda and mu are real. V and mu u are corresponding eigenvectors of lambda and u, and we have to demonstrate that u and v are orthogonal to each other. To that end, a v is equal to lambda v, a u is equal to mu lambda, multiplying the first equation on the left by u transpose and that of the second by v transpose, and subtracting, same trick that we used in the previous claim. So, this equal to that, because these two are the, if I took this is a scalar, this is a scalar, these two scalars are same. So, the difference is 0. So, I am going to take the eigen representation. So, this is lambda times u transpose u, mu times u transpose u. Therefore, lambda minus mu is u transpose u, and but I do know lambda is not equal to mu. So, this inner product, this can be true, 20 can be true only when u transpose u is 0. That means they must be orthogonal. Wow! We will use this, but we are also proving it. So, what is that where we are right now? Let me quickly summarize what we have done thus far. We introduced the notion of what is called the invariant subspace. We verified eigenvectors are invariant subspaces. We talked about general distribution of eigenvalues for a general matrix. Then we specialized to symmetric matrix, we specialized to positive definite matrices. We are trying to pin down the properties of eigenvectors and eigenvalues for a real symmetric matrices. What is the only difference between symmetric matrix and symmetric positive definite matrix? For a symmetric matrix, the eigenvalues are real, it can be positive, negative. For a positive definite matrix, the eigenvalues are real and positive. Except that, the symmetric matrices and symmetric positive definite matrices inherit many of the properties that are common to both. What is the first property? The eigenvectors of real symmetric matrices are real. The eigenvalues of a real symmetric matrices are real. Then the eigenvectors corresponding to distinct real eigenvalues are orthogonal. Now, a slight notation. Let D be Rn, denote a invariant subspace of A. A invariant subspace of A means what? If I picked any vector V belonging to D, A V also belongs to D. That means if this property in mathematics is called closeness. If you take two numbers, I get a number, a real number. If you multiply two numbers, you get a real number. That means the real number system is closed under addition and multiplication. So, if the set D is such that if I picked a vector from D, if I multiply by A, the resulting vector also belongs to D. That means it also falls back on the same space D. Such a spaces are called invariant subspaces. Invariant subspaces are characterized by a sense of closeness. So, okay, so this is the sign that they use for orthogonality. So, if I say x y is orthogonal, that implies x transpose y is equal to 0. So, D is a subspace. D perpendicular means what? It's a subspace of vectors in Rn that are orthogonal to D. For example, if I took a two-dimensional plane, this is x1, this is x2, every vector along the x1 axis is orthogonal to every vector along the x2 axis. So, if I say that D1 is a set of all vectors x such that a set of all vectors y such that y is equal to alpha times the vector 1 0. Vector 1 0 means what? Is the y component is 0. So, this is the vector that lies along the x1 axis. So, any vector which is in the form y is equal to alpha times 1 0, that is D1. Any vector that lies along here, this is D1 perpendicular, is a set of all vectors z, which is such that z is equal to beta times 0 1. The first component is 0, second component is beta times 1. So, these two spaces are orthogonal to each other. D1, one-dimensional space along x1, one-dimensional space along x2, these are orthogonal, and that I denote by the symbol D perpendicular sign. So, what does it mean? If I picked any two vectors u belonging to D and v belonging to D perpendicular, that inner product is 0. So, what is the idea here? If D is an invariant subspace, D perpendicular is also an invariant subspace for the matrix A. So, if D is an invariant subspace for the matrix A, D perpendicular must also be an invariant subspace. So, for any UV belonging to Rn, U transpose A U is AV transpose U. So, if U belonging to D, then AU belongs to D, because D is an invariant subspace of A under assumption. V belongs to perpendicular to D, therefore, this belongs to D, this is in the perpendicular space, so V transpose AU must be 0. From AV transpose U is equal to 0, it also follows AV belongs to D perpendicular. That means, if V belongs to D perpendicular, AV also belongs to D perpendicular. That means, if D is A invariant, D perpendicular is also A invariant. Every non-null invariant subspace D of A contains the real eigenvectors of A. So, that is the next claim. Every non-null invariant, non-null means a null space is essentially 0 vector. So, here non-null means it has non-zero vectors. Let K be the dimension of D, then there exists a n by k matrix B whose columns constitute orthogonal basis for D. Please understand, any subspace of dimension K can have K bases. Some bases are oblique, some bases are orthogonal. So, I am assuming that there exists column vectors of the matrix B that constitute the orthogonal basis for D. Since D is A invariant, it is immediate that AB must be equal to BE. That means BE is a set of all vectors which are linear combinations of a K by K matrix. So, that is the implication of that. If please understand, the span of B is a D, because B and D is a span. or D is an invariant subspace. Every invariant subspace must have a basis. So the columns of B constitute the basis for the subspace D, and D is A invariant. So if D is A invariant, it is immediate that AB as a matrix is a matrix which can be obtained by BE, where E is essentially a K by K matrix of real coefficients. Then B transpose AB is equal to B transpose BE, but B transpose B, the columns of B are orthogonal, so B transpose B must be equal to identity, so that must be equal to E. So here I give you a recipe for computing E. That means if B is the basis for the A invariant subspace D, then AB is equal to BE, where E is simply B transpose AB. B transpose AB we can generally consider as a transformation of A. This is called, in general, called congruence transformation of A, congruence. Similarity transformation, congruence transformation. So this is an example of a congruence transformation. The proof of the claim 4 continues. Since A is real and symmetric, now please understand, A is symmetric, B transpose AB is symmetric, and B transpose E is symmetric, so E must be symmetric. Why B transpose A is symmetric? B transpose AB transpose is equal to B transpose A transpose B. Product of the transposers taken the reverse order. This is B transpose AB because A is symmetric matrix. Therefore, this is a congruence transformation. This is a symmetric matrix. Therefore, E must be a symmetric matrix. So that means there exists a real symmetric matrix E such that for every lambda x, E x must be equal to lambda x, where x belongs to Rk. X belongs to Rk. So we proved that E is real and symmetric. Real and symmetric matrices have eigenpairs. So if lambda and x are the eigenpairs of E, Ex is equal to lambda x, where x belongs to Rk. Therefore, AB of x is equal to A of B times x is equal to AB of x is equal to B times BE of x, which is equal to lambda times B of x. Lambda times B of x. So what does this tell you? If you compare this with this, it tells you if x is not 0 and the columns of B are orthogonal, which we have already assumed is orthogonal basis for D. If orthogonal bases are also linearly independent, it follows Bx is not equal to 0. If Bx is not equal to 0, by virtue of this, Bx is an eigenvector of A contained in D. So look at this now. AB of x must be equal to lambda times B of x. That means B of x is an eigenvector of A that is contained in the invariant subspace. So what is the claim? Let's go back to the claim. Every non-null A invariant subspace D of A must contain a real eigenvector. So D is an invariant subspace. B is the basis for the invariant subspace. The columns of B forms the coordinate system for the base for the invariant subspace D. So now we have shown that every invariant subspace must contain an eigenvector. The set of all eigenvectors of a real symmetric matrices form an orthogonal basis for Rn. That's the claim 5. Recall that every real symmetric matrix X is endowed with at least one eigenpair. We have already shown that. Hence, for some n, let V1, V2, Vm be the orthonormal set of eigenvectors which form the basis for the subspace D of Rn, and D is the invariant subspace because every eigenvector associated is an invariant subspace. So I have D perpendicular Both of them are A invariant. Hence, there is a vector Vm plus 1 belonging to D perpendicular such that V, V1, V2, Vm are eigenvectors of A. That means, if you give me a set of m eigenvectors, I can now compute the m plus 1th eigenvector. So, starting with m is equal to 1, using this inductive argument, we can obtain an orthonormal basis for Rn of eigenvectors of A. I hope you are all with me now. I hope you are all with me now. It is a sequence of improvements. A sequence of improvements. We first showed that there exists a basis for the invariance of space, and we showed the existence of every invariance of space must have at least one eigenvector, and we extended that to the whole matrix. Now, what is claim 6? Every real symmetric matrix is diagonalizable. That is the ultimate goal. So, this is one of the last results from matrix theory we are going to prove. Let A be a matrix, let V1, V2, Vn be the set of orthonormal eigenvectors of A. Vi is equal to Vi lambda I. Lambda is a diagonal matrix. We have verified Av is equal to V lambda, V transpose V, Vv transpose is I, and hence V transpose Av is lambda. V transpose V is Av lambda. And that is the diagonalizability argument. That means every matrix, look at this now, every matrix, what is this? Set of all n by n symmetric matrices. This is a set of all diagonal matrices, diagonal, set of all diagonal matrices. Every matrix A can be mapped into a diagonal matrix, and this transformation is given by V transpose AV. So, that means for A there exists a matrix V such that the matrix A is equal to this, and V transpose is V inverse because V is an orthogonal matrix. So, you can also write this as we can also write this as V inverse AV. This transformation is called similarity transformation. So, this essentially tells you every real symmetric matrix using similarity transformation can be transformed into a diagonal matrix. This is called the diagonalizability of real symmetric matrices. So, every real symmetric matrix is diagonalizable. If every real symmetric matrix is diagonalizable, the diagonal elements of lambda are eigenvalues of A. On the top of it, if you give me the matrix is symmetric and positive definite, I am going to say every symmetric positive definite matrix can be diagonalizable with non-zero diagonal element along the principal diagonal of lambda. This appendix follows from the development of chapter 8 of a book on algebraic graph theory by Gottsel and Royal. It's a very nice book. The book is on matrix theory applied to graph theory. Computer scientists deal with graph theory, graph theoretic models. And the major tool in the analysis of graph theory in this book is matrix theory. So, that is what it is called. So, you have graph theory, you have algebraic graph theory. Algebraic graph theory deals with properties of graphs using matrix representations of graphs. So, in this book is a very nice book if you want to learn about applications of matrix theory to graph theory. But in this course, we are interested in application of linear algebra to data science problems. But matrix theory, that means matrix theory is applicable to several areas of activity. I am now trying to prove every result. Another classic book is Matrix Computation by Golub and Valdon. This second book deals largely with numerical algorithms. It's an excellent book. It belongs to every researcher's table, and it gives a wealth of information for computing the eigenvectors and eigenvalues of real symmetric matrices. So, in sum, what is it we have accomplished in this module? In this module, we have shown the proofs of several claims we normally take it for granted, And what are the special things? I will quickly summarize. Eigenvectors are invariant subspaces. There is a notion of algebraic multiplicity, there is a notion of geometric multiplicity. Algebraic multiplicity relates to the number of times a number is the roots of the polynomial equation. Geometric multiplicity relates to the dimension of the space spanned by the eigenvectors corresponding to a given eigenvalue. The geometric multiplicity is always less than or equal to the algebraic multiplicity. The eigenvalues of a general matrix can be real or complex. Eigenvectors of a real symmetric matrices are always real. Eigenvectors corresponding to real symmetric eigenvalues are orthogonal. We brought the notion of invariant subspaces. Then we showed every invariant subspace of A has an eigenvector. Then we developed the notion of an eigendecomposition. The eigendecomposition led to the final result on what is called diagonalizability of real symmetric matrices. These are absolutely fundamental results. These are used repeatedly in data science, as you will see in the rest of the modules that we are going to talk about. So, I believe in the early stages I would like you to take some time off to be able to understand the proofs and the claims that constitute the basis for further analysis and further applications of linear algebra in data science. Thank you.